So thank you, and hello everyone. Yeah, our names have been introduced. We are Ron and Freddie. Freddie, maybe you also say hello.
Hello.
I'll take the first part of the talk, and Freddie will take the second. I'll quickly start to describe the context in which the following work was created. Freddie and I worked in the middle of last year for a thing called Frontier Development Lab. This is a 2-month so-called research sprint. It's organized by various organizations you see at the bottom. Mainly, basically, it's by a company called Trillium, which do it on behalf of NASA and ESA. And they gather several partners to assist with things like processing, data, and all the other things. I will come back to it over the course of the talk. We were part of the challenge called Earth Science, and the basic question is for our project where the rivers in the US are flowing. And we have created over this course several hydrology map based on satellite data and based also on LiDAR data, LiDAR aerial data. This was the team, so it's not just Freddie and me. This is us. As you see, it was COVID times, so we were not really in the water. So we were all in our rooms. The only water was the sweat because it was a hot summer. But our team consisted, this is explained here better, of 4 researchers, which are Dolo, Gonzalo, Hannes, and me. And basically some support, lead guys, mentors, which are on the bottom, Freddie, Guy, Jonathan, Kevin, and Ignacio. It was a bit really of a wild ride due to time zones and all these organizational parts. So generally it would have been based in California, but many of us, in fact, were based in Europe, while others were in the US. So we had some organizational fun with it. But now let's start with the topic. So here you see basically some historical context for what we did. So the current framework for the mapped US stream network is based on mapping campaigns, which were mostly conducted in the 60s and 70s, but also, as you see here on the bottom, even earlier. This was a lot of in-field work. And it's over half a century ago, and only based on very few quantitative images like is possible today. From an ecological, sociological, economic, and regulatory standpoint, more information is needed on the time varying characteristics and categorization of streams in the network. You see here the different types of perennial, intermittent, and ephemeral, which are related to the groundwater and the surface water. And the WOTUS challenge is focused on using modern methods and a range of geospatial data to refine and update the categorization and characterization of streams at continental scales. The challenge asks the questions, can we use machine learning on the satellite observations in combination with modern high-resolution terrain data and other ancillary data to fortify the sparse observations currently available via stream gauges? Here you see basically a connection. There is like streams which are not clearly visible due to their non-permanence, also I wanted to say one thing. There is no slide for it. I wanted to cover this also. I'm sorry to skip back. Our work was basically sponsored here by our team, especially. There were multiple in this Frontier Development Lab context, by the USGS, which posed the challenge of doing the stream mapping. We had the computational resources by Google Cloud, and a lot of the data, not all of the data, but a lot of the data was provided by Planet. So much also for naming the institutions and not only the persons. So basically, while the US Stream Gauge network is one of the densest and most comprehensive of its kind in the world, it still only represents point samples at discrete locations. So basically, there are these gauges which collect data at certain locations. And although this network covers major streams across the US, supporting science, disaster response, planning, and policy guidance, these observations only over a small fraction of the US streams network. So indeed, 97% of the remaining streams, here shown in red, so this is a bit like these ecological assumptions of how many species there are, and many not mapped at all, have no observed data on frequency or flow or current state, and have functional categorizations that have not been updated in over half a century. The amount of streams missing from the current data set represents a huge unknown volume of water whose eventual assessment is required for reliable drought and flood prediction. In the next section, we outline the data and methods that we have used to go from the satellite images to water detection. So basically, we have this approach. I will go later more detail into what the Wassernetz is. We use basically this imagery with high temporal and spatial resolution, as well as terrain data. And in the end, basically, we can create water probability maps, which are derived from the imagery directly. And based on the terrain data, we can derive the reaches, which are basically based on some watershed and other algorithms, the real flow accumulators. And in the end, we have been juggling with a couple of ways to visualize the data and what is the most, the best to communicate. In the end, we found these percent water per reach maps, as you will see later in this talk, as a very approachable form. Because in the end, this I will go into right now. And I haven't given this talk in half a year, and therefore I didn't check. Yeah, obviously the nice animation where these satellites will be flying around, I won't be able to show because I just forgot how this was managed. I don't know, Freddie, feel free to interject, but I think it's not worth the effort, right? But imagine a very nice video here with these satellites moving and all. So this is basically what you see here.
You can press play. I think if you click that.
Sorry? Louder?
Can you press play on the video?
No, it looks like a screenshot, in fact. It doesn't. My browser also struggles with YouTube, so I don't even try. I don't try. So let's talk a bit about the context coming from a remote sensing perspective. This slide here goes not into so much detail because it was also oftentimes used in front of geo people, but there are basically a couple of developments in the last years. So the very classic thing you see on the left side, it says Landsat and Sentinel-2. So these constellations get data at medium to high resolutions between 10 and 30 meters. And they have very wide swaths of hundreds of kilometers. They serve a wide range of ecological and overall scientific applications. But the ground resolution is limited, and for this reason especially, and you see also you get some images per month. So the revisit rate of some of these satellites is of a single satellite is like 10 days, 16 days. Then there are constellations where the revisit rate then gets lowered. But overall, it's not the super highest frequency, and it's also not the super highest resolution. The good thing with these data, if you are interested yourself to try around, they're generally free. So if you Google for this stuff, you will definitely find some platforms where you can use them. For our study now, the nice thing is that we were sponsored so well, and that the sponsors enabled us to use really commercial data, which is generally hard to use. And on the one crazy hand is the MAXA data from the Worldview constellation, and basically they are tasked, so they don't generally generate this certain set with a certain revisit. but they can be ordered. And when they are ordered, they are there. And then they have resolutions of even sometimes below 0.5 meters. We had a data set of which we in the end sampled to 0.5 meters. So the use cases here are generally not a long-term monitoring, but it's more like you have a specific target, maybe an airport or whatever. Also, obviously, a lot of military applications, which you then want to pinpoint. But then there's a very nice compromise, which is Planet, which was one of our main sponsors. There you just get, and with just get, I mean us, because they were so nice to provide us with data. You just get daily data with a 3-meter pixel resolution. And even more so, the data set we received is a very new processing product where they merged it with other data sets, and it had basically no artifacts, which are generally very common in remote sensing, like clouds, cloud shadows. The atmospheric haze, everything was more or less gone, which was very handy, and it was just AI-ready data, and we could just start our experiments. Obviously, there's then some obviously there's no magic happening, and the data must come from somewhere. I don't want to go into detail, and there were still limitations, but considering how remote sensing generally works, it was very useful data set. So I want to also talk a bit about this. As part of the study, this is a screenshot from it. We also created this very like a small click dummy thing to get a better impression on the data, where we then could create these chips and just look at it, also to illustrate what we have at hand and where there might be some artifacts in it. What you see here is basically how many lines is it? Maybe even a year. So our data set consisted of 2 years of daily images over 4. I will show later which AOIs in the US. And what you basically see here is like one image, a chip, a very small chip from the very big image, just to see, just to illustrate the the seasonality. But you get one per day. We basically had images, and as you see here nicely, also with a river in it, that's how the color spectrum develops over the course of the year. The Planet data, I must say, is RGB plus infrared. So what you see is obviously just the RGB. But yeah, it's daily data. How do they look for comparison? So basically, in the top left, there's the Maxa at 0.5 meter. You see everything in it, basically, at least it feels like. In the top right, there's Sentinel-2 from the same date. It's much too coarse for tasks like mapping smaller rivers. Planet data is obviously the compromise. And then also here to show it, there's the LiDAR DEM that we had available, which was based on an aerial campaign. But obviously, it's a one-time sporadic acquisition and not in a repeat cycle. Now let's go at least in some detail into the neural network structure that we used. So basically, we had different input sources. We had the daily Planet acquisitions. Then we had the DM. We did also very many experiments. We basically took all the different puzzle pieces and built our networks and ran all the tests the way it is generally done. And now I'm just wondering when the next slide will appear. Here it is. Then we had another standard UNet where we took the very high resolution data of the Maxa and created also water probability maps. And in the bottom we did the modified UNet, which is basically we have the multi-temporal steps, and we don't just throw in one image. We did tests with throwing in an entire batch, like as a stacked image, but we also used then variants where we basically did like 3-dimensional convolutions to address the temporal component. And these were basically the different networks we took. Especially into the Wassernetz, I think I will also come back in the following slide. So what is here now? There's the different AOIs that we had. These AOIs are based on different basins. So a basin is basically like a yeah. There's at one point, and I'm sorry I miss again the hydrological termini. At one point, there's where all the water flows out. Obviously, it gets aggregated from all these points in this area. And what you see here colored in different colors are the corresponding subbasins. We chose these basins yeah, based on what was given to us with regards to data, but they are also considered especially representative here, at least of the Western US. They had different properties. So with regard to, snowfall, etc. Plus, obviously, the data was in some way pre-processed. Basically, some study areas were easier to handle than others. All yeah, they all have like different topographic and climatic conditions. That is obvious, and some have more canopy. Canopy was also a big challenge. We had, I assume, we will also see in later slides again, like the canopy shadows were oftentimes misclassified with water, and also yeah. Depending on the time of year, topography can also create shadows, etc. So one can discuss as much as one wants about sampling strategies, especially also in the geosciences. We had 2 months time, and we had also people assist us with the labeling from the USGS. So we, in a way, we were a bit picky, but we couldn't, fulfill all the pickiness. But that's now in the end how it was. We had, of the different study sites, certain locations annotated. I assume there will be, let me quickly skip just to make sure. Yeah, there will be another slide who says the exact labeling strategy, but we basically have here some train test splits where you see that we try obviously not to mix in and from direct neighborhoods get the same samples from testing and training. So I would, there's an argument to be made that our accuracies are really conservative estimates because we didn't make it too easy in the end. Yeah, one can, and we had also discussions about many of these factors, including obviously things you see here. So the polygons were labeled on images by the MAXA satellite. The data was not perfectly geolocated. There were shifts in the data. I don't want to bore you and also don't want to get too frustrated again, but nothing is ever perfect in data science and compromises need to be made. We found good solutions. We did some shifts. We did some other tricks. I think Freddie could talk much more about it than I could. But importantly, and also maybe as a recommendation, because I see it in segmentation tasks, I've seen it not only once, and especially in the geosciences, it's always good to, to have an anti-class. So we are interested in water, but obviously the best idea is to as well annotate, adjacent areas or similar areas as non-water. This is basically what the USGS guys also provided us with, despite the earlier mentioned yeah, also discussions that were had. But basically that's really needed, that there is like water, non-water categorizations in order to enable the algorithm to make the distinction and to learn which class looks like what. Yeah, here we have a lot of small patches. I need to quickly digest this slide myself. So you see the different data sets. The MAXA data set was just a single. It would not be right to say it's a single point in time because it was big study sites, which were then also collected over different at different dates. So there's some chaos in the data set when one image is taken a month later than the other, etc. But for Maxa, there was basically one image at all over all these study sites, one aggregated composite image. While for Planet, we had the, like I mentioned earlier, wall-to-wall coverage of daily images. And then we had the LiDAR data, which we then also derived different other products from. So from the DEMs, we also then had slope maps and other derivatives. I think in the end, we had like 5 layers derived from the elevation model. And yeah, here you basically see some of the examples how they look in the different data sets, the water, non-water images. So in the end, the very nicest results, or obviously it's also a political issue, which one is now the nicest. It depends on the exact research question you might have. But to get an overall impression on the data, this slide we had before, doesn't matter. I will directly skip to this because this is more interesting anyway. We saw earlier already in the earlier talk some similar like encoding decoding structure. We have here, it's really based on a UNet overall, where we have different heads. For a while, we also called it the Hydra because we have here the DEM going in, which gets like due to the different ground resolutions. Let me make one step back. We obviously take images from the same extent geospatially, and then you have different resolutions. And when you have different resolutions, you need to take care of this because then you have a different number of pixels at the edge. So what you see here is basically our way of dealing with it, which is that the DEM, which had a higher resolution than the Planet data, received one, let's say, initial convolution and max pooling, etc., before then concatenating it with the time series data, which in turn also received the 3D convolutions because it's a time series data set. And in the end, we basically stacked it all, and then we ran it through through a unit type architecture. And in the end, basically, as you see on top, the water probability maps were created. Then there's not so much more to say. If there are more questions later, we'll be happy to answer it. And I think also Freddie can go into more detail if there are specific questions. And I will hand over to Freddie now anyway, because we are basically at halftime roughly.
Awesome. Cheers, Ron. Do you mind if I share my screen instead? Because
No.
I think we do have a video.
Feel free to hijack.
Ready? There's some noise coming from your microphone, maybe when you hit buttons on your laptop.
How about now? Test. Is that better now?
Maybe you're using your laptop microphone instead of the headset.
That's a good point. Let me fix that.
Sounds like it. You're kind of hitting the keyboard and the mic. And now it's gone. Yeah, it's better now.
Good. Excellent.
Yeah, can you type something?
Okay. Is that better now?
We still hear you type.
Well, that's normal, I guess. But I mean, is it like distracting? I will just
not
try
to me.
to avoid
I got used to it.
I will just not type it. Let me share my screen. Sorry about that. I guess I have not to press my pad. I have to just gently press on it. Cool. All right. Okay. So yeah, we've seen this slide. Okay, let's talk a little bit about the metrics. And let me just keep track of time. We have 18 minutes left. All right. So how does a supervised machine learning model learn? It does need some signal, and this is like our study, our model is what you call supervised machine learning. And supervised machine learning means that the machine learning learns from some ground truth that typically a user or some expert provides. Ron talked a lot about types of what is the data and what are the labels. And here I'm kind of repeating the same story here. We've got, let's say in the top row, we've got planet. Chip is basically another word for a patch. Sorry for the background noise, my dog is barking. There's a middle row, which is like what would the corresponding model output look like. And here it very much looks like a heat map where each pixel is like some value between 0 and 1 saying this pixel is likely to be water or not. And then on the bottom row, you see visualizing a difference between what the model predicts and what the ground truth is. So if there's a misclassification, we would signify this with either a yellow color in case we're talking about a false positive, or a brown or a red color in case that's false negative. So if it's purely blue, it means that's a true positive. So that's like a correctly identified water. If it's brown, if it's correctly identified land. So as you see here, something that's distinctive is that the polygons that are from a land, so like the brown polygon, they tend to look kind of big and squarish, and that's because when people were drawing land polygons, they had a lot of land to draw them from. So if they were drawing river polygons, they have very narrow spaces to draw them from, and they have to be quite precise when they're drawing the word polygons. So this is an example of sparse labeling. Some people might consider it as a form of weak labeling, but there's a lot of types of weak labeling, but let's not get into that. But this is a form of sparse labeling in the sense that you can't ask from a human being to annotate the whole, hundreds of square kilometers of imagery, because land is easy, but then when you get to the water, you have to really find and like delineate the borders of the river very precisely. So if you ask them to do this for thousands and thousands of miles of rivers, that's obviously like we don't have enough labor capacity to do this. So what we can do though is we can ask an expert to annotate key parts of a river network that they consider hard enough, because then if they can do it with their human eye and their expert knowledge, and their labels are accurate and the imagery is good, then a computer vision model can do it too. That's kind of the rule of thumb. If you can understand with your human eyes, then using the same data that you expect the computer to use, then you can expect a computer to learn that too, assuming that you do this again and again many times, you have enough data to do it. That's generally just in computer vision, right? In supervised computer vision. Now, but how do you monitor all this stuff? Like, how do you give a signal to the computer that it did a good job or not? You take each annotated polygon and then you measure how many, what's the number of pixels in it? That's in the denominator. And then you count how many pixels it got correct. That's in the numerator. So essentially that fraction represents the fraction of the polygon that the computer predicted correct, because each polygon has a number of pixels in it and each pixel has a class, as we saw. It's a semantic segmentation problem. Now that is one approach you can use, and that is a naive one, and I will explain why is it naive. Now if you see the larger polygons here, the land ones are quite large. So if you put equal weight to a land polygon as to a border polygon, then most of the pixels are going to be on land polygons. So that means that in order for the model to do a good job, it needs to learn to get the land polygons, the land pixels right. So there's going to be a slight bias, a slight preference towards getting the land pixels correctly. And because we have relatively fewer river pixels, that's those are kind of going to be like marginalized, and the computer is not going to pay too much attention to them, because in order to decrease its loss, it will just put more emphasis on the land pixels. So in order to tackle this, what we did is that we took every polygon, we normalize it for its size. That's what you see in the lower equation here. Essentially, that metric represents what what fraction of the polygon the model got right. So again, the top one, if you minimize by the top one, it's measuring what fraction of pixels it got right. But in the lower one, we're measuring what fraction of the polygon got right. So essentially, every instance, every polygon, if you think of it as an instance, now is being assessed on the merit of the fraction of its area. So by using, I'm just going to focus, basically, I'm just going to talk about all the models I'm going to talk about are models that are trained with this metric. That's what our loss is. And all these diagrams I'm going to show you are basically focusing on this one, on the fraction of the ball. So the big picture result is this one, where on the y-axis, on the x-axis, we have the accuracy per polygon, as I described. And on the y-axis, we have the different, let's say the same model, model being, we call it waternuts. And here is not a study where we're trying to say, okay, well, this is the state-of-the-art model, or we're trying to say, well, this is theoretically the best possible model you could use. What we say is we're taking some box standard semantic segmentation model like a unit, and we're asking, based on what data can we solve this problem? How well can we solve this problem? So we have three types of data sets here. One is a model that is trained on purely Maxar data, does 0.5 meter resolution, very, very, supreme resolution as you can get in the commercial satellite imagery work. And then you have, on the bottom, you have a planet data model. Sorry, this is a bit misleading. You should actually say 3 meter, no, 0.5 meter. And that is a model trained on 3 meter per pixel resolution. And it's natural to expect a gap, because when you train a model based on low resolution, there's less features to learn from. I think it's a very intuitive result, right? But then what is more interesting is that if you have a model that is trained both on planet imagery and complemented by LiDAR, all these like LiDAR byproducts that Ron talked about, and the LiDAR information is purely, the height of the bare earth and the height of the vegetation on top of the earth, which comes at 1 meter resolution. And by the way, this LiDAR, actually the raw format is point clouds. So this kind of goes back to the earlier talk. And from the point clouds, there is a derivative product that gives us a raster. So from the point clouds, they actually derive a raster, which is like per pixel, you get like an estimate of the height of either of the bare earth or the vegetation. So we could have also worked with point clouds, but the idea is that would have required a lot more computation. So we just get that byproduct readily from there's like standard procedures to turn the point clouds into a raster. And if you train a model with this fusion of products, you get somewhere in between, which kind of makes sense, because it basically says there are some cases where the lack of spatial resolution in the imagery, that's where the LiDAR information can act as a stand-in and complement in the form of altimetric data, like the shape of the land, if you will. This is basically just a table, but in numbers form. Now I'm going to show you like a breakdown of the earlier shot, but now per AOI. And this is quite important, because some AOIs are harder than others. Harder in what sense? So let's say, think about the shape of the land, and in some cases there are many hills that cast shadows, elongated shadows, or they're like very tall trees casting shadows. There are also, in some areas, there's more vegetation. This is what we call geodiversity, right? So areas that are more geodiverse, they are also called, I should say, areas that are less geodiverse. They are more optically cooperative. So they're just easier to the eye, so to speak, right? South Dakota is very easy to the eye. It's a very pretty land. It's very flat, relatively flat. It doesn't have, it's not very challenging from a remote sensing perspective and from a computer vision perspective. So what we see is that all models are relatively high performing, but within the area you can see also the same kind of ordering, the performance, like Maxar is the best one, LiDAR, plus planet is the second best one, planet is the third one. Same kind of picture in Upper Colorado, but Idaho is the one I was referring to when I was speaking about geodiversity and optically non-cooperative areas, where especially the smallest streams have a lot of vegetation around them. There are a lot of hilly areas casting shadows. We see this especially affected the models that are trained on planet data. Now, of course, the Maxar model is also suffering. That's not immune to this geodiversity, but if we start decreasing the spatial resolution of our input training data, we really see now the importance of spatial resolution. If you take that away, then you have a useless model. And even if you complement it with LiDAR data, it can only do you so good. It can only help you so much. Okay, now I'm going to do a further breakdown. Now, for each AOI, I'm showing you on the x-axis a breakdown by a characteristic width. This is what I mean by width. So let's take every body of water, and with a state-of-the-art virtual ArcGIS ruler on purple, I'm gonna measure some sort of like characteristic width of the body of water, right? And we do this for every annotated body of water that we have, and then we can do this breakdown. So we have all these different bins. Let's say for streams that go, above 100-meter wide, all the way down to the smallest streams that you can put your feet across, between 1 and 2 meters. So because with very high resolution imagery is something you can map, but you can only map it with Maxar data successfully. That's what this figure shows. Okay, so as you see with the breakdown, you start to notice as you go to streams that are thinner and thinner and thinner, you start to see the performance degrade. The performance degrades more visibly for models that are trained on planet and on planet data. And again, this is something that we expect. But more interestingly, where the planet model started to degrade is around the point where it's like, at below 10 meters wide. And that kind of makes sense if you think about it, because anyone who has kind of like done any signal processing course, or it's intuitive to say that if you want to detect a change in an image, that change needs to manifest across 2 pixels, right? So this kind of goes to the classical sampling theory, where in order to detect an object of a certain frequency, you need to sample twice as frequently of that frequency. So that's what we see here, is that if you want to be able to detect rivers that are 5 meters wide, you need to have a resolution that is at least 2.5 meters imagery. And with planar imagery, because it's 3 meters per pixel, that means that it's physically impossible to render any river that is smaller than 6 meters wide. Yeah. So this is what we start to see here, like the performance of any planet-derived model is degrades. However, with Maxar, that is not a problem. Of course, the picture is slightly different across South Dakota and Idaho, because South Dakota is more optically cooperative, and Idaho is much less so. Okay, so this is pretty much the same table. I'm going to skip this one because this kind of dives deep into the classification performance of the polygons in average, and this is just basically to say that if you're if you calibrate, what threshold do you need to choose in order to have this much recall and this much precision. So this is a very typical analysis people do when we talk about classification. I think you've seen this image. In summary, basically we have 2 types of models. One is trained on planet daily captures and fused with LiDAR data. And at the bottom we have another model that is trained purely on Maxar imagery. Both of them produce a heat map, a water probability map otherwise, which is always at 0.5 meter per pixel. And you might ask, why would the planet-based model be a 0.5 meter per pixel, even if it's a 3 meters input? That is because our annotations come at 0.5 meter per pixel. So when people annotate these things, they're actually looking at maxar imagery when annotating. So the annotation is going to have the same resolution as the native maxar resolution. Okay, so just a quick comparison here. This is Becker et al. It's like a kind of a famous, I think it's like a Nature paper from 2016 where it's considered like the golden standard in water mapping. This is how well it does it. We're showing you here some Google Earth Engine image, and the Becker et al. Model is kind of comes out of a Google Earth Engine, and you can like use it. Anyone can use it publicly to see how well it maps rivers at certain streams. It's pretty bad. However, our model does pretty well at distance stream, so we beat the state of the art. Now, I want to show you very quickly, illustratively, our whole pipeline in a few slides. So, pixel streams. How do we go from pixel-based predictions to reach level predictions? Okay, on one hand, at the beginning we have satellite imagery coming in. What you actually see here is a false color rendering. So that means that false color means that you get a number of bands in the satellite, and you can decide what to map to RGB the way the computer renders it. So the way what this shows is really focuses on vegetation. If it's red, there's a vegetation. You get this image, and then the unit gives you a water probability map. Every pixel has a probability, and this is what it thinks where water is. And on top of that, we also have the LiDAR information where every pixel's height. This is actually coming from us. It's an input. We don't actually predict this. So this is coming from the LiDAR, which is raw point cloud data. And what hydrologists typically do is that they take LiDAR and they derive flow lines. So these white lines are actually flow accumulation lines. There's like this standard algorithms where they basically do a kind of like a follow where does the path of the steepest descent, and then where would water theoretically flow to, and where would gather, and then that's how these white lines are derived. And then what they do is that they chop these white lines according to where they branch out, and then every segment between branches, between every branching this is called a reach. So everything that is like of a particular specific color is a reach unit. So think of it like a geo-referenced unit, and every unit has a collection of pixels. Now we can take the water probability map that I told you earlier of the unit, and then for each reach that I showed earlier, we can do sort of like a little mathematical integration and say for every reach, how much water probability, like how much water does the neural network predict for that reach? And this is what you see here. For every reach, you see what is the percent that is covered of that reach that is covered by water. I have half a minute left, and I want to close up with this beautiful video of what if we do this for every daily image. It all culminates to this wonderful video. And this is what we call a dynamic hydrology map. I'm just going to let it play out for about 2 years. It's only going to take 5 seconds. So in short, we have a byproduct of all the culmination of all this data that shows us, based on a series of images, daily captures, we can now know what percent of each reach of each part of a river, what percent of it is covered by water. So this, think of this as a time series, a geo-reference time series. And now this as a tool is pretty powerful because you can analyze this time series, and you can say where you can expect water to be at any time of the year. You can do all kinds of analysis. You can say, oh, this is where I expect like little water in times of drought. This is where I can expect a lot of water in times of floods. This is something that deserves much more analysis. And we created a tool that enables hydrologists to do this kind of analysis. Yeah, I'm going to stop here because I think we're just out of time, and happy to take any questions.
Thank you so much, Ray and Ron. It's time for questions. There was one coming from the chat from Jiexi. For planet data, if the polygon contains both water and non-water for 1 or 2 M streams, is the polygon annotated as water?
So I'm just trying to find the chat. Can I stop sharing my screen for a second?
Sure.
I also, if the polygon contains both water and non-water for 1 or 2 meter streams. Is the polygon annotated as water? Generally, these are scales, so I don't have it visually in my head spontaneously right now, but I would say that on these scales, it's very hard. The annotations were based on streams that were generally a bit bigger than this, but maybe Freddie, you have an opinion on it?
Well, if you wouldn't create such a polygon to begin with, that if a polygon turns out in reality to actually have both types of things, then it's a bad polygon. Like, if an expert would never give a polygon that contains both things, just because like you don't want to confuse the model. And it's just like in the way you collect data is just kind of more logistically simpler to say I'm going to draw one polygon, but it's going to be one thing, like one type. Of course, you can make a composite polygon, but like this is more of a, I guess, data collection thing, right? But just for simplicity here, we would say every polygon that we have in our collection is of one class. Like we know for sure all its pixels are of one class.
In practice, there might be small shifts due to some but this, no one would sit down. The polygons need to be per class.
Yeah, and of course, like there might be also kind of like some errors. Like sometimes what happens is, and actually we had this in our case, like these annotations were collected where people were looking at maxar imagery. But then when you take the annotations and you try to apply them to planet, there might be some misregistration. Like the satellite imagery is not always perfectly, let's say, orthorectified, or the coordinate systems are a little bit off. So some streams dry down through the year and so give predictability of the drought. That is the hypothesis. It's something that we haven't gone as far as studying systematically. I mean, this would be the topic of a Nature kind of level paper where we do this for many streams around the United States to see if there's actually any predictability in this time series, both for the sake of droughts analysis but of floods. But generally, it's also a matter of not just like protecting people, but it's also water management, which is like a very precious resource. And it's something that you want to be able to monitor at the near real-time level. This is what the planet imagery affords us. Like there's no other satellite out there, not to advertise Planetube, but there's just no other constellation out there that gives a daily capture across the planet at 3-meter resolution. It's just, there's nothing like that. Not for a while, won't be.
Freddie, there's another one about whether we solved the shadow casting. I don't know if after FTL there was more stuff. Yeah, we had a lot of
program,
ideas.
Yeah.
We had a lot of ideas and few times. One would be to just include another class, shadow, which would make things easier potentially. Others were more complex, like including, the angle of the sun and seeing where there might be shadows. And
we can do like physical modeling. Yeah, we can do some like some kind of like Poorman's version of ray tracing to see, well, here you have the bare earth, here you have the vegetation, just cast some light and see where the shadows cast. And that's could do that. But actually, maybe I was wondering, maybe if the people who are kind of used to working with these like 3D physical models and that do rendering under the hood as well, maybe they have some ideas.
Just a minor question. I was wondering, how did you do your neural network architecture diagrams that you had on the slides? Is that a particular tool for drawing?
Yeah, those? it's all state of the art Google Slides.
Good, thank you.
It's just getting most bang out of the buck we have. There is no GitHub. There's a GitLab, private GitLab, but it's just too dirty to release it out to the public. So we didn't have enough time to clean up the code. We barely had time to get proper data agreements to share the data, but we just got licensed to release the data at some point. We're going to release the data. All I'm going to say is that there's going to be a proper effort to create a code base and data set after WORUS 2.0. So we talked about WORUS 1.0. We just got funding for a follow-up project to take care of all that stuff that we have problems with. Can the slides of the talk be made available? Of course, yes, of course. Yeah, actually, oh yeah, I forgot to mention this. So there's a preprint called Pics to Streams. If you just Google Pics to Streams, the way you saw in the slides, you'll find the archive paper, which also has a link to the video that I just showed you. I'll just type it now in the chat. Pics to Streams. There you go. Just Google that, you'll find the paper. So where can I check if GitLab is released? If you may, it's private. You can't. Thank you for the link. Oh, well, after the end of the second follow-up project, so I would say in around 2 months probably. That app was also, yeah, that's a pretty handy app. Yeah, there's no like consensus of how best to draw a neural network, right? It's there's just so many out there.
All right. I was wondering if you have any tips for somebody who wants to get started with machine learning on Earth observation data. Any beginners tips? Where do you start to dive into this vast topic?
Yeah, I mean, there's public challenges out there. There's things like SpaceNet. SpaceNet is a great start. Like there's now like iteration 7 of SpaceNet, which is they're using not daily, I think monthly planet products for change detection of like footprints of buildings. But yeah, there's like previous space nets. They were around typical like land use, land cover detection, classification, object detection. These are very typical problems in Earth observation. I would say maybe counting them is a slightly more exotic one, but segmentation and object detection are like kind of like what people mostly do. Time series is not so much of a hot topic because it's very hard to tease out a time series out of monthly captures unless we're talking about large scale changes. Like if you're talking about, you know, how like the development of a city, then yeah, monthly makes sense. But daily captures that you would need, like for instance, to map the intermittency of a stream, that's kind of like it's only enabled by daily captures. So I think what we're going to see in the future is these products being released out in the world all of a sudden, mainly from Planet, because like they want to show that the products are useful. They're going to release more and more of this free data, and then that will enable people to do more interesting stuff. Yeah, there's this problem in the satellite industry that the main commercial companies are like hogging their data. Then even though there's tons and tons of like petabytes of data there that no one is ever going to buy, they don't release it out for some reason. There's this kind of culture, but Plan is slowly changing that.
Freddie, please, the names you mentioned just now at the beginning, could you put them in the chat? My English is not native English.
SpaceNet. So SpaceNet is SpaceNet 7 is what you wanna like. It's kind of like, think of it like Kaggle for Earth observation.
Are you kidding? There is a Kaggle for Earth observation? No way. Okay, yeah. So how it is? You put it in the chat? No.
Yes, I just put it in the chat. SpaceNet.
Oh, awesome. Thank you.
So regarding mocks, ESA does a lot. If you just Google for ESA and mock, you will find things. Overall, you will find things if you look for Earth observation and mock. Yeah, some are a bit specific, depends on what you want. Many don't even have anything to do with machine learning. But yeah, there's quite some stuff.
And yeah, the tools of the trade are things like GeoPandas, Rastereo, DASC, X-ray, even though the last two are not just specific to Earth observation, but they're very handy when we're talking about very large imagery that doesn't fit in memory. So if you want to read part of the image, you don't want to necessarily load the whole image in memory like you typically do with ImageNet. I don't know, Ron, I'm blanking.
GDAL, obviously, OGR.
Yeah, like Rasterio basically is like a kind of like a GDAL wrapper, I guess.
Yeah.
And there's like suites that people use in industry. This ArcGIS is the one that is proprietary, but there's an open source version of it called QGIS. Pretty amazing. Does very much everything that ArcGIS does, but it's just the UI looks more like an open source project, if you know what I mean.
Ron, the acronyms you said, could you please write them? It's hard for me to spell things, you know, easy with E, with A, with. Thank you. I'm sorry. There is another question, minor question. Someone asked how long? Yeah,
how long? Oh yeah, I said 2 hours on. We had access to V100 GPUs, so just a single V100. Was it one V100 or? Yeah. I want to say yeah, one V100 2 hours. Yeah, because we didn't have that many annotated polygons, so even though the whole of the imagery that we have access to is a lot, it only made sense to use whatever was annotated.
Yeah, for us, the challenge would be the inference, not the training, basically.
Yeah.
All right, folks, if there are no urgent questions anymore, let's call it a night, and let's have a round of virtual applause for all our speakers and the great talks of tonight.
Thank you.
Yeah, thank you. Really nice.
Thanks for having us.
Yes, thank you all.
Thank you too.
Yeah.
Yeah. Have a good
we
night,
hope
everyone.
to see you all soon again. We're doing this every 2 months, and yeah, stay healthy, everyone. Take care and have a good night.
Take care. Bye.
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 Bye.